Okay, we have started questions on the homework.
Yeah, homework for chapter 6. No questions? Everything was understandable? Yeah. What?
Number 12.
Okay, what does it say? What does it say? Number 12.
So it's dn1 over dt equals negative n1 plus 0.1 n1 n2.
Plus 0.1 n1 n2.
And then it's dn2 over dt equals n2 minus 0.2 n1 n2.
Okay, this is problem 12. Homework for chapter 6. Okay, what are we supposed to do with it?
Find the steady states, draw enough lines in a graph, and arrow diagram.
Okay. How do you find steady states? Set both equal to 0. So that minus n1 minus plus 0.1 n1 n2 equals 0. And I have n2 minus 0.2 n1 n2 equals 0. How do I solve that?
Solve for one of the variable.
Okay. What do I get?
0, 0, and that.
Not the answer. What do I write next?
You can now do like n1, take it out, and then take the first equation, and then take
In the first equation, I have,
take n1 out.
right, I know that n1 is equal to minus 1 plus 0.1 n2. So this means n1 equals 0, or
Negative 1.
n2 equals what? Right, so there are two situations. Either n1 is 0 or n2 is 10, and then we figure out what do each of these situations mean in equation 2.
Are you going to yell at him for using
So
bad
then we have, if n1 is 0, in equation 2,
And 2 is 0.
I get n2 is 0. Right, because this whole term dies.
Yes.
And so this gives us 0, 0. And then I say if n2 is equal to 10, plug that into the second equation, and I get 10 minus, well, n2 is 10, so that would be 2n1 equals 0. So you get n1 equals 5. And so here we get 5, 10. So these are our two steady states. Now we're going to want to draw the null times. It basically means I'm going to want to graph I'm going to want to graph n1 equals 0, and 2 equals 0, and these two straight lines. So let's see how to situate. Maybe let's try to dead center, see how it looks. This is n1, n2. I have n1 equals 0 is the vertical, and 2 equals there is the axis just as normal. Now when I draw the inside, what is this? This is just we've solved for this before. This is just n2 equals 10.
Yeah.
And so n2 equals 10 would just be a horizontal line going through 10. And in this one, this just means n1 would be, what's that? N1, is that 5? Yeah, so n1 would be 5, which is just the vertical line. Right, that's like me drawing y equals 10 and x equals 5. And so we just get that cross pattern. So now to do the arrow diagram, again, we just test a point in one of these regions. So I test one of these guys. What do I know is over here?
Down and left.
Yeah, so something obvious, like 15, 15, or 10, or 15, 10, or something like that. And you test it in each of these. So if my n2 is 10, what is that? No, 10 is not there. I want a 10 here. 10, 15 is what I'm testing. So if my n2 is 15, what would I have here? Would this be positive or negative?
If your n2 is 15,
Yeah,
this would be negative. No, it would be positive.
it would be positive.
Yeah.
So let's stretch here. So I know here, that's my dn1, right? So that's going to the positive, that would be to the right. If I plug in this guy, n1 equals 10, what would I get?
Siobhan, if the point is 10, 15,
It'll be negative.
wouldn't it
Negative.
Hmm?
be? If the point is 10, 15, wouldn't it just be positive one? I think.
Yeah, I'm doing 10 here and
Oh,
15 here.
Okay. I mixed up y and x and y. X and y.
Yeah, n1 is the x, n2 is the y.
Gotcha.
And so in the second one, it actually is negative, so it goes down. And in the same way, remember that this line came from the n1 equation. This is the n1 null time. This one came from the n2 equation. This is the n2 null time. So if I go over here to this region, I jumped over the n1 line, so what's going to happen?
Left and down.
Left and down. And if I jump over here, I jump over the n2 line, what's going to happen? Up and left. And if I jump over the n1 line, up and right. So as you might see, something like this, if you're started something here, it actually will sort of bring you into a circle.
Ooh.
Right? And this is kind of, they usually use a system like this for a predator-prey model. Predator-prey model. Right, where none of them are going to die out. They keep just cycling. Eventually, the predators increase to the point where they start to run out of food, and so their population starts to decrease. But then this other guy, now the food population starts to increase, so the predators can increase again. You see the two populations just starting to go in a spiral. Yeah.
For the test, how do we know when to go right or down?
What do you mean?
Because before we knew where to always start. The top right, we always start with left down. But this one is the opposite.
I don't think so from the picture.
What are you talking about?
For the starting arrows.
Yeah, with the arrows.
Yeah? What about it?
You had to always put in a certain rate. You gave us the rule, you're like,
Right. Did I give you rules that deal with equations that look like this?
No.
so an equation like this wouldn't be okay to say.
No.
Alright, perfect.
Thank you.
So we can assume the other arrows, right?
As long as it looks like the situation that I gave you in class, yes. Everything I told you applies to that.
Alright, perfect.
Took me 10 hours instead.
Yeah. Math is super specific. Okay, if I give you rules to deal with a certain set of equations, they deal with that set of equations. Something looks different, don't assume all the rules apply to it. Yeah. What? 19? Yeah, what we were doing before doesn't apply to things that look like this. It applies to things that look like a logistic model with two populations. This is not that model. It's not going to have the same rules. So here we just have to go back to basics and actually test points to see what's going on. So 19. What does it say?
Oh, DIDT equals
DIDT.
0.01 SI minus 0.2.
Oh, this is like the infection model thing. We won't need that yet.
Doesn't we have homework that's like, it has nothing to do?
Some of these homeworks are assigned your own homework.
It
They're sitting there like, I never learned this. It's not.
You learned all the principles needed to solve them, but it's not important when we have time constraints, because I actually want to do review today. So we have to make time for it. But obviously, you shouldn't find a problem with me wanting you to know things outside of a little box, right? Is that like a problem? We just want to know about this and nothing more, Javon. Only chess is on that, and only talk about that, and only goes homework on that. We don't want to know about the outside world.
If only
I don't
that.
want to know about what's in the
That sounds
box.
great.
How do we pass the class?
We're very conservative.
Yeah. You scientists, I love your curiosity and your zest to explore. I love it. My future scientists and doctors and all that stuff. Oh, I only deal with this kind of brain tumor. If it's that kind of brain tumor, I'm sorry. You're just gonna have to die. I just know this set of equations for that kind of brain tumor. I didn't get tested on that one, so you're out of luck. Thank you. Thank you, doctor. I'm glad I came.
That way we all have a job.
Okay, any other questions?
Unless it's going to be on the test. I don't think so.
Are you taking review questions from the finals yet?
Sure, we can do a review problem.
Yes.
So those are from the finals? Yeah.
Can we do variations of the test question? Like, you see the test? Just change the numbers of the problems, and then we could do each one.
Well, that's what the finals are. That's what the finals are. Yeah, questions on that?
What is it? Spring Club.
Now remember, the test covers chapters 4, 5, and 6, right? So qualitative methods,
Yeah.
the population models, meaning you have to know harvesting, logistic, and the Malthus model, and then the last one, the systems of equations. So that's what the test is on.
Spring Club is number 10.
So spring, okay, let's do a spring 09. We're doing number 10.
Do you want to see it?
Okay, so it says consider the competition model of these differential equations. So it's a chapter 6 problem. It says dn1 dt equals 0.25 n1 1 minus. This is 100. This is 50. dn2 equals 0.1 and 2. This is 3. Find the steady state solution of the system, blah, blah, blah. Okay, all right. How do we do that?
Right, the steady state.
How do we find the steady states? Yeah, in equation 1,
It's 2n1.
right, either n1 equals 0, or
Or n.
this whole thing equals 0.
Which is
100.
I can multiply by 100,
Times
n1, 2 and 2. So n1 is 100 minus 2 and 2.
1 minus n2 over 100.
Don't we have to state if, whether it's competitive or not?
They didn't ask for that here.
Oh, cool. You'll do that too.
They never asked for it.
But you will.
No, they did in part C. In part C, they asked for it.
Actually,
So they asked us to do it last. So that's because they don't know Lowe's method.
Loser.
In Lowe's method, you have to go through the whole thing to figure out, or you have to do a competition table. So yeah, in 2, I just plug in each of these situations. So if my n1 is 0 in this equation, I would get, if n1 equals 0, then I would get either n2 equals 0, or I would get n2 equals 100. So this gives me 2 steady states, 0, 0, and 0, 100. If n1 is equal to 100 minus 2 n2, I don't like the chalk, whoever used whatever chalk they used before this.
Are you gonna go to their house to do the thing like last time?
What?
Remember you said you were gonna stand outside the last person's house and be like, use this chalk.
Yeah, I'm gonna have to start tracking them down, seriously. I forgot. Okay, so if this is true, what's gonna happen? We plug it into this guy. And so what we have n2 times 1 minus n2 over 100 minus 300 minus 6n2 over 100 equals 0. So I have n2 equals 0. Or I would have, multiply this by 100, I would have 100 minus n2 minus 300 plus 6n2 equals 0. So that, was that lightning or?
Yeah.
I've seen it like 5 minutes ago.
There was a UFO flying around.
Lightning is fine, it was a fire drill then.
Oh, it was a fun girl.
So this just gives us 5n2. So this is 5n2 equals 200. And I can divide 200 by 5, and I get what?
200 by 5 is 40.
So now I have n2 equals 40. This means if I plug in 0 here, my n1 is 100, which gives me 100 comma 0. If I plug in 40 here, this becomes 80, so my n1 equals 20. And so this is 20 comma 40. So those are all 4 steady states. And that answers part A. Part B says a collection of phase curves for the system is shown below. Based on the graphs, how would you characterize the stabilities of each steady state solution you found in A? Briefly explain your responses.
That was a real question.
Okay, so here apparently we didn't have to draw the null lines. I'd asked you to draw the null lines, but apparently here they just gave you the phase plots. Really, they actually did the null lines for you, but they don't show it, and they just had a bunch of points. So what you can say about this system for each of these steady states, from the graph, what we can say about this, from the phase plot, I know that, notice that there are a bunch of steady states where we approach this guy, the 0, 100. And there are some times when we approach the other guy, the 100, 0. But notice there's like this barrier here, where if you're below that barrier, you go towards this one, and if you're above that barrier, you go towards the other one. So that sort of means that these guys are semi-stable. Right? From one direction you approach them, from the other direction you run away from them. That's the definition of semi-stable.
so what does that
Is
mean
it
when
not
we're talking about
competitive?
competition?
This has nothing to do with competition.
Oh,
It says characterize the stability of the steady state solutions.
Okay.
Right? So you'll also notice that 0, 0 is also a steady state, but you pretty much never go there. This is an unstable steady state. Right? The other guy is the 2040, they never really tested that. That guy also is unstable. They just want you to say stable or unstable. Now remember what stable means, you always go towards it from both directions, from any direction. Semi-stable means sometimes you approach it, but from another direction you run away from it. Unstable means you always run away from it.
Okay.
So
So that's
Yeah, so I wouldn't particularly ask a question like that. I'd ask it more like what you would do, what we've shown in class. In part C, it asks us for the, whether it's competitive or not.
It is.
You could actually tell that from this graph, right? Because the situation depends, right? Depending on where you start, one population would survive versus the other. So obviously from this graph, you'd be able to tell that it's competitive. But you could even do Lowe's method. So what you would do is, notice that there's a 3 here.
Yeah.
That seems to mess up a lot of students. Because they're like, it doesn't have a smaller denominator.
You just
Remember,
have
the
five.
form that I give you is important. Having a 3 there is the same as having a 3 here. Right? So this is the smaller denominator. And so the arrows go this way and that way, and you end up with depends. So C says it's competitive. Use by Lowe's method. Or you could explain, according to the phase plots, you know, sometimes you approach this phase state instead of that one. So yeah, if I gave a problem like this, I would have actually to draw the null lines and give you an initial condition and all that stuff. The standard sort of questions. Okay.
So nothing like stable and unstable over there?
No, I don't think I'd ask a lot.
Oh, Javon, I have a question.
Yeah.
If we don't take a department final, correct?
Right, you take my problem.
So let's say
Because of my class.
if somebody in 209 did take the department final, would by Lowe's method be valid?
Yeah, because even if you took the departmental final, I'd still be the one grading
Okay.
it. Yeah. Yeah, no one's gonna do the extra work here, Javon, it's your student, you grade it. And then I'd have to make up 2 solutions to grade your paper. Kidding. But I'd grade it anyway, so anything that we do in this class will be valid. Other questions?
I have a question. Is it possible that the laws listen that 2 denominators are equal? Or?
Well, it's possible for denominators to be equal, yeah. You mean, so you can do this? Yeah, so the method wouldn't apply in that case, and you'd have to go the long way route.
Don't put any of those on the test, please.
Other questions? Oh, we just need to remember what they mean. So, semi-stable means
One approaches.
you approach from one direction, but go approach from one direction, but run away from the other. Right? This one means you always run away. Right? And stable would mean you always approach. Right, so those are basically the ideas. It's just like, it's basically we're taking the same concepts that we did in the one differential equations case. Right, so if we had a steady state where even if we're above or below we approached it, we call that guy stable, right? But there was another steady state where we run away from it from one direction, but from the other direction we approached it. We call that semi-stable, right? And someone who was like unstable would mean you run away from it in either case, right? So this guy's the unstable. So that's the idea.
So, but to really understand this, if you, what could you say about population really? That means that if you have a little more of this species here, this species will end up winning?
Yeah. Yeah, remember each of those dots in that graph gives you an initial condition. It assumes, okay, what if we start with these population sizes? What would happen in the long run?
Okay.
So you can sort of see that, okay, if we start off with a lot more N1s than N2s, the N1s will win. If we start off with a lot more N2s than N1s, the N2s will win. Okay, other questions?
Very cool.
Anything else from Spring 09 that bothered you?
You know what falls on the eight number 3?
Fall of 8. Problem 3. Okay, so it says use geometric analysis, so that means qualitative methods, to analyze the differential equation dy dt equals 5 minus y plus 3, y minus 1. Right, so here they told you the steps. Graph g of y versus y. G of y is just another name for the derivative, remember that. That's just y prime. Sketch the curves of the initial value. So it's basically telling you to go through all the 4 steps that we normally go through. So let's just go through them. So first we need to find the steady states. Are they steady states though? We'll set that equal to 0, right? And then we get y equals 5, y equals minus 3, y equals 1. What about inflection points? Let's find the derivative of that. Now this guy is we call our g. So let's find g prime.
So you have to combine it and then?
We can multiply out if you guys want. Do you prefer multiplying out? Or?
Yes.
Yes, please.
Okay, let's multiply out. Multiply out 2 at a time.
Yeah.
You could apply the product rule here though, but let's multiply out since it's
Robert, so
Minus y plus 15.
it actually wouldn't be that
Minus
bad.
y squared
You say
minus
that.
2.
You could show us
So
both and then we'll decide.
okay, so let's multiply out these first 2. So I get 5y
Plus y.
Plus 15.
plus 15
Minus y squared
minus y squared
Minus 3y.
minus 3y
This we can do.
times y minus 1, which equals,
5y squared.
well, these I can combine, right? Just think of this as minus y squared plus 2y plus 15. And I'm going to distribute each of these. So I get y times that minus y cubed plus 2y squared plus 15y, and then a minus 1 times all of that. So it's a plus y squared minus 2y minus 15. Combine these again. So this is a minus y cubed
Plus 3y.
plus 3y squared
Plus 13y.
plus
Minus
13y
15.
minus 15. And so now I can find g prime minus 3y squared plus 6y plus 13. And so now I need to set this equal to 0 for inflection. Does that factor?
No.
13.
It doesn't factor?
Can you use the AC method?
Yeah, or we can use like quadratic formula. Minus b plus or minus the square root of a squared minus
4 AC
4 times a times c
over
over 2a. So those are your inflection points. I don't particularly care to find out what those are.
So we leave that on the exam, it'll be fine, right?
You put a hashtag.
Well, I'd probably give you nicer numbers.
1, 2.
So now those are inflection points. Let's start to graph this guy. What does this guy actually look like? So now we're going to draw the stability graph,
It's cubed. So it would have 2 curves.
right? By the way, the stability graph would actually be the graph they asked for in part A, right? So this, we have the intercepts, which is minus 3. That's a steady state. At 1, that's another steady state. At 5, we have another steady state. It's a minus y cubed graph, which means I know it looks like what? It's coming down this way and going down that way, right? So I'll test the insides. If I test something like 0 into this function, what do I get?
You get
I get a negative, right? So I'll be under here. If I plug in a number like here, I would get
like a 2.
like a 2.
Okay.
Positive.
Everyone would be a positive, so I'd be up here. So I know my graph would look like, so I know that's my graph. Now our inflection points would be whatever that guy is, and it'll be like whatever that guy is. It would be that. All right, this would be the one with the plus radical, this would be the one with the minus radical. Okay, now we analyze the steady states, the day's axis for that. Well, we're gonna have to do it anyway. So here, how do the arrows look?
Smiley face. Oh, to the right,
Right,
to the left.
left. So that's a stable steady state because we're always approaching it from both directions. This one.
To the left, and then to the right.
So this one is unstable. We're always running away from that steady state.
That's that.
This one.
To the right, and then to the left.
This one is also a stable steady state. Okay, so now it says sketch the solution curve for y of t if our initial starts at 3. So from this, we're going to jump right to the solution curve. T, we have steady states at -3. We would have our inflection point would be somewhere right here. We also have a steady state at 1. That's a steady state. That's a steady state. That's an inflection point. We also have an inflection point at 5.
How do you know?
That's steady state. And our inflection point is, it'll be somewhere in between 1 and 5. That's our IP right there. And it says we want to start at 3. So where's 3?
Between 1 and 5.
Right, but is it in this region or that region?
Really good question.
I guess we have to know what these are.
Yeah.
Luckily we can use calculators. What are these?
3.309 and negative 1.3.
Negative 1 point or
3.3.
3.3. Okay, so our 3 would be below this point. Okay, so what does the solution curve look like here? We're above the inflection point. We're like right here. Well, we're right here at 3.
So it goes away from 1 and towards 5.
So it goes away from 1 and go towards 5. So we're going up. What's our concavity like down here?
Up.
Concave
Down.
up like a smiley face.
So
We
it's
switch
up.
to
So it's
frowny
up.
face. To
Up like a
level
cup,
off.
down like a fire.
Yep, exactly. And that's it.
Okay.
Yeah, that's the complete question. Like everything they asked for here, we actually did. Right, so part A is to actually draw this graph. Part B is to do these arrows. Part B was to draw this solution graph. And part C, we showed the concavity here. Yeah. Other questions?
The 6B, it says something about rates on that one.
When populations N1 is 30 and 40, determine whether each population is increasing or decreasing. Oh, you literally just plug it into the equations.
Okay.
Hey Javon, just a quick question. Geometric analysis literally means
Means
graphs.
this is geometric analysis. It means qualitative analysis, and geometric is the same thing. Yeah, it means graphing, basically. This is spring 2013. Six. So we are given here our dn1 dt equals 0.02 n1. N2 is 0.04 n2. Now they asked you to find the steady states. That was part A. And determine which are stable. Okay, so that wasn't the part that we had trouble with. Part B says when n1 is equal to 30 and n2 is equal to 40, determine whether each population is increasing or decreasing and at what rate. You literally just plug those numbers into here. So this would mean that your rate of change of the N1 population would be 0.02 N1, 1 minus N1, which is 30 over 60, minus N2 over 90, which is 40 over 90. And this would give us something, dn2. Zero 4 and 2, 1 minus 40 over 80 minus 30 over 40. What does this give me? 0.56.
Yeah, 7.
And this one? That one would be negative, right? Would be negative what? Okay, so from this we can conclude that N1 is increasing at a rate of 0.567 and 2 is decreasing at a rate of 0.4 or minus 0.4. Yeah, that's it.
So does that mean that N1 will survive? And N2 will die eventually?
In this situation,
And that-
that's what it would seem like. Other questions? No more? Thought I'd be bombarded with questions. You should have a review, Now we have a review. What's up? What? What? Now you guys have nothing to say?
You're a great teacher, so.
Do you think there are any questions we should go over? Do you have any questions we should go over?
How about your feel, of class, give us something.
Well, any question like this, I'm going to ask you to draw null lines. I'm going to ask you to do phase plots. I'm going to ask you to tell me what's competitive. So even if the question in the final doesn't ask you to do that, you can do that as extra practice. Because if I'm going to give you one of these, and I'm going to ask you for all that stuff. The same way I did the examples in class. I'll also give you the geometric one, like the one we did before with the g of y.
Are you gonna post the video today?
Yeah, there are 5. So
Is it gonna post the video?
let's see what I So one of the questions are going to be like this. I think I gave 2 of the geometric ones,
And the geometric ones,
and I gave maybe 2 population models, if I remember right.
How long will we have?
So obviously the logistic model, I'm going to test you on that. That always comes on a final too. But then I'll test you on the other one. Probably, of course, a harvesting model because malthus is just too easy. So yeah, you can probably expect one on like a harvesting model, a logistic model, one of these, and 2 geometrics maybe.
Can we do a logistic model?
Yeah, and
Are you gonna try to teach us how
So
to do
it's
there was one.
So
geometric analysis, some population questions.
yeah.
Which one is
Can you find a logistic one?
Yeah.
I have a harvesting one, I think, if you want to do that one, if I live in this, because I did a logistic.
Okay.
Number 8.
Okay, so this is spring 08, and we're going to do number 8.
Is that number 8?
Yeah, spring 08, number 8.
That's logistics.
And it's like that, number there. This looks like harvesting. Spring 08, column 8 says, a shrimp farm in Thailand starts with 3 million shrimp, a natural growth rate of 12% per year. The owner harvests 420,000 shrimp each year. Set up a differential equation to model the fish population, solve it, and find out if the fish population will be completely depleted. Complete your answer to 3 decimal places. So let, whatever we want to call it, P equals the shrimp population, current shrimp population. What does the differential equation look like?
P equals R. No.
dPdt.
Right, differential equation has to have a derivative in it.
R
Yes.
P K P.
RP minus H, right? What is the R in this case?
You have.
What did it say?
You guys don't have the thing?
No, I don't
I'm
have.
the only one giving you questions, so.
I don't just want to tell you, I want to know if you guys can actually read it and figure it out.
All right,
So
read
read
us
the
a
proper-
sentence.
read the
We'll let you
sentence.
know.
A shrimp farm in Thailand starts with 3 million shrimp, is that it?
No.
This is not.
Has a natural growth rate of 12% per year.
Yes.
Put 0.12 here. Okay.
Good
The
job.
owner harvests 420,000 shrimp each year.
420,000 is H.
Is
Yes.
that plus or minus?
Plus. No, no.
Harvest
plus.
means he's
taking
taking
them
them
out.
out.
We're not farmers, you can't write that.
Yeah.
You don't know what that means.
I'm a farmer.
Okay, so that's the differential
The only one
equation.
that's
Do we
gonna
know
get
an initial condition?
Yes.
Yes.
I still
The 3
have
million. They start with 3 million.
1, 2, 3.
Okay, so that's the differential equation. Now it says solve it to find out if and when the fish population will be completely the shrimp population. Well, that's a typo. That said fish, but it should be shrimp.
You see what I mean?
You're like, I don't know what's gonna happen to the fish population. I just know what the shrimp.
That's legit.
I'm not a magician, damn it.
Imagine somebody wrote that on the final. Like,
Like, damn it, Captain, I'm a doctor, not a.
you're a farmer.
So what? Okay, so what are we gonna do here?
So dP is divided by P minus 35, 350, hold on, 1, 3 million. What?
Take out the .12.
We can take out the 0.12, right? If we factor that out,
Yeah, that's what I did.
what do we get here?
P, okay, so 3,500,000.
3, 5, and then 4 zeros.
500,000?
5 zeros.
Yeah.
Yeah.
Okay, cool. So now we have dP over P minus 3,500,000 equals 0.12 dt. And we integrate both sides. This becomes ln of p minus 3,500,000 equals 0.12 t plus c. Raise both sides to the e. I would end up with p equals c e to the 0.12 t, and then plus this 3 million. And so now I need to apply the initial condition to find the c. So I know that when I plug in t equals 0, my population is 3 million. So I end up with 3, 1, 2, 3, 4, 5, 6 is equal to c e to the 0 plus 1, 2, 3, 4, 5. And so my c would be what? Minus 500,000?
Yes.
Yeah.
And so finally my equation for the population is minus 500, 1, 2, 3, e to the 0.12 t plus 35. So it says solve the differential equation and then find out if and when the shrimp population will be completely depleted. How do we figure that out?
Well, t is equal to 0.
Right, so basically we want to set is p ever equal to 0. Right, so let's actually set it and see if we can actually solve for it. Right, so 0 is equal to minus 500, 1, 2, 3, e to the 0.12 t plus 3500 t. So what does that mean?
It should track.
Basically I take minus 3,500,000. I would end up dividing by the coefficient of that. 500, 1, 2, 3. And I'll end up with e to the 0.12 t. Right, so these zeros cancel.
You get 7.
So I basically get 7. And then I take ln of both sides,
Yeah.
and that would give me 0.12 t. And so my t, it actually has a solution. Is equal to ln of 7 over 0.12, which is approximately what?
16.2 years.
What?
16.2 years is what?
16.3 years.
0.2.
It is 16.2.
Okay. So yes, the population will shrimp will die.
Can we predict climate change for this?
No, the equations would be a lot more complicated.
Well.
Was that the whole question? That was the whole question. It said to 3 decimal places. It said to 3 decimal places. So what would be the other 2?
2159. So.
156.
So that would be your answer. So yes, it will be depleted after that many years.
I found the logistics one.
We found a logistic guy.
Yay!
Oh my God, so excited.
Did you hear the sarcasm?
This is spring 09. And this is problem 9.
No, fam. I don't got this. I know it's very interesting. No part of me does got this.
Is it all coming back? Are we remembering?
Yeah, I'll definitely.
Okay, the growth of population is described by a logistic differential equation. They'll always tell you it's logistic. I'm going to tell you it's logistic.
And the equation
The
will be given?
The intrinsic, no, the equation is not given.
The answer is given.
The natural growth is 4%. The carrying capacity is k equals 350. Write a differential equation to model the population. What is the general differential equation for a logistic model? We're using-
RP.
Are we using P or N?
Truce.
Because
T.
Q.
N.
1 minus C over P.
Okay, so that's the equation. I'm not going to tell you the equation. You need to memorize that. Okay, so they said the natural growth rate is 4%. So we put 4% here, right?
No.
P is outside. I mean,
The R.
So 0.04.
0.04 P, 1 minus P over this. Told us K is 350.
3, like,
Okay. So now they said write a differential equation, da 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 da. Okay, we're done. For each of the following initial values, use the first and second derivatives of the population function to sketch the graph. The graph should clearly show the long-term limiting behavior of any curved cavity Bayes-Law graph on the same set of axes. So basically, no, we just close our eyes and we draw this. They just want to draw the graphs. So what's the stability graph going to look like?
P is equal to 0, and P is equal to 350. I forgot. I don't know.
Yeah, P goes like,
What does the graph look like?
Is it a problem?
one's at 0.
So parabola, like this?
No.
Like what?
No, I'm confident.
Oh, it always looks that way.
What's this point? This is 0. Where's the inflection happen? What's this stability?
It's left and right, so it's essentially.
Right. 0 is always unstable. This one,
This is definitely.
always stable.
You said
Right.
it's always like this, right?
Yep. At this point, we're just basically closing our eyes and writing. Okay, so that's the stability graph. What's the solution graph look like?
Everything approaches 350.
T. So 0 is one steady state. And 350 is the other one.
Did it give us a point?
That's a steady state. They did it in part B. 175 is our inflection point. They gave us 3 initial conditions. So they said draw the solutions on the same set of axes. So one starts at 100. One starts at 300. And one starts at 400. And this is the solution graph, which is what the axis defined. So what does the 100 look like?
It goes towards 300.
It's gonna be.
Yeah, but concavity here,
Concavity
Yeah.
up and then.
concave up like a smiley face,
And then.
down like a frowny face. This one,
It goes towards 300, concave down.
concave down, all the way towards 300. This one,
It's
It
gonna
goes
go
concave
down.
up.
up
Oh, yeah.
towards 300.
Yeah.
So yeah, that's what it asks.
And so we get like 15 points from this.
Yeah,
Cool.
just like that.
Oh,
And you'll use, and then you'll give us those points, right?
Huh?
That we need to, the reference points, like those points.
I might ask you to do the calculations.
maybe it's too much, right?
Yeah, 'cause it's just too easy to give away those points. So I might ask you to show
No, it's
finding
not.
the steady
You
states.
know how much I struggled?
Right here. Here you
Leave it
get.
here, man.
Huh? Struggle to do that?
Yeah, I struggled through everything in math. Leave it here.
So P is equal to 0, right? And then
So you said this equals 0, which means that P equals 0, or P equals 350.
That's
So that's a
actually easy
point.
20 points, right?
Yeah.
Yeah.
It's like 1 of 5
Stop
questions.
calling
It's
it
like
easy, please.
It's memorization.
I got the memory of an Alzheimer's patient.
What does that have to do with
My idea.
What, you could only remember logistic equations?
I like statistics.
That's what you guys should be like. Even when you get Alzheimer's, you should be like, I still remember a logistic equation. Differential equation, I can solve it.
God
I
forbid.
don't know my name, but I know how to solve it. I don't even know who you are, but I'll tell you how to solve this logistic equation.
So bad stuff. Oh my god.
Any other questions?
What else were you asking?
I told you what I asked.
Well, it's not gonna go up, no, it would always go down, right? Forever? If it's logistics?
In a different method.
The only way for this to go that way is if this is negative. Then everything flips upside down.
Don't do that.
Stay positive.
How much have you joined the track?
Yeah, nobody
Yeah? Quiet down. What?
For that question, I gave you like, the initial value is 350, and that's like the steady point. You just.
You would literally just stay there. At 350, you'd stay on that line, 350. Right, because at 350, your growth rate is 0. So you're just staying there. You're not growing, you're not decreasing, you're not increasing. You'll just stay at 350.
So the environment can only sustain 350 of those.
Yep. That's the optimal condition.
And how do people determine K? Can we do that?
It's usually empirically.
What does that mean?
It means by experiment. You watch it, you measure it, you take statistics over a long period of time. Yes, there are always bonus problems. Only finals though, not bonus. Alright, let's move on. Let's do some more of chapter 7. Chapter 7 is pretty long, so I want to just keep hacking away at it until we get through it.
We're going to have one test.
No. So last time we ended at the histogram, I think.
Yep.
Okay, so chapter 7 continues. Last time we had the histogram showing the distribution of grades. This was our title. Should always have a title. On this side we had relative frequency. We had like 0.1, 0.15, 0.2, 0.25, 0.3. We had the 55 bin, the 65 bin, the 75 bin, the 85 bin, and the 95 bin. And these were the grades. So this one was at 15. Then we had, this one was at 30, I think. This one was at 25.
Okay.
The 85 was at the 20. And this one was at the 0.1. Alright, so that was the histogram we ended up with last time. So now look what happens when we connect the tops of the bars at their center point. Alright, so I just go over my histogram and then I'm just going to find the center point at the top of all the bars. And I'm going to connect them. I end up with another shape. It's like boom, 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 boom.
I love Frankenstein.
And this guy is also a very common kind of graph. It's called a line chart. Line graph or line charts. Again, you'll also have the relative frequency here, grades here. Should also have a title. Right, but it's just another kind of graph. Now, line charts are nice because they help us see trends, right? So this graph gives rise to the notion of the shape of data. Right? So we're going to talk about the shapes, and it's sort of like something that a line graph would into. You can have all sorts of shapes to these line graphs. Right? So let's just talk about some kinds of shapes. One important shape. Emphasis on important. And when we get to chapter 14, you'll see why it's so important. Is the symmetric bell curve. This guy is super useful. And if you've done any sort of research in biology or anything like that, chances are you've seen a graph like this before. Sort of looks like a normal distribution curve. You might have heard of that. If not, don't worry. When we get to chapter 14, I'll tell you about it. So basically, it's completely symmetric around this center, right? This is the mirror image of that part. Right? This is called a symmetric bell curve. It's a very important shape. It's a very nice shape because we can use it to approximate other shapes, and we actually know all the math behind this curve. We can talk about the equation of it and everything. We know everything about this curve. And so anything that behaves like this curve, we can get a lot of information out of it. So it's a very important shape because we have a lot of models that deal with it.
Is it still one where the first two squares are like 34 point something and the next two are 60?
Yeah, I think you're thinking of like the 65, 95, 98 rule.
That's the one.
Yes, it's similar. We'll get to that rule eventually. But yeah, symmetric bell curve is a very important shape. So if you have a bunch of bars and you connect the tops and you get something like this, that's actually pretty good because we actually can tell a lot of what can happen with that data set. It's a very important shape. Another reason why it's an important shape is because it's very ubiquitous. There are so many different kinds of data sets that follow that shape. You'd be so surprised. Anything complicated would follow that shape, basically. Simpler things would have simpler shapes. So a lot of statistics that deals with, for example, anything to do with human beings would normally shape like that. Right? So how many people get cancer from smoking? This would be the curve, right? You'd have sort of a peak where a lot of people do it, and then your chances kind of branch off later on. So, we'll talk about that later. I'm getting ahead of myself. Just want to introduce shapes. I want you to note though, shapes can be misleading if you set things up incorrectly. Example, not enough bins, or the bins are too wide. Right? You can just make things so simple that you can't get any information from it. But in general, if you set up things nice, you get nice shapes where you can talk about the data in terms of these shapes that we might have mathematical equations for. Another thing to notice from this line chart, which I erased, or even that graph, the graph has a peak. Now, peaks are important, right? What does that peak sort of tell you?
The majority of...
Like the majority, like a lot of things fall into this range, right? The peaks sort of tell you what you should be looking at. Like most things would be at that value, right? This indicates the typical situation. right? So you see, like, if you're plotting a data set and it looks like this, you realize that around this value, there are a lot of things will fall in this range, right? So figuring out where that peak is, which you can see pretty easily from a graph and not so easily from like a set of numbers or a huge table of numbers. When you actually draw this graph, you can point, oh, there's a peak right there. We should be focusing on this part of the data right here, because most things fall there, right? So you can get that pretty easily from a line graph. So it has a peak, which sort of indicates the typical value of the data set, which leads to the notion of central tendency and averages. Which is another very, 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 very important topic in statistics. Should I define this? Sure.
It's very important.
Yes. Central tendency refers to tendency of data to cluster around a certain value. This central value is approximated by a number that we call the average. Right? So all an average is just an approximation of this central value, right? It's an approximation of the typical value of a data set. There are many averages, tons of ways you can get to a typical value. We'll look at 3 of them. One is called the mean average. Right? This is what people usually think about when they think average, right? But it's not the only average there is, right? So this is called the mean average. Right? So, do I have an example here? Sure. Well, let me write the definition first. The mean is the sum of all data points divided by the total number of data points. Right? So you can think of your test grade as a mean average, right? Total number of points you can get is 100, and then I add up all the points you get out of 100, and I find an average, and this is your grade. That's a mean average. It's not particularly mean, but too much puns. Okay, let's move on. Let's do an example. For the data set, here's a data set 12, 3, 2, 15, 12, 9, 8, 12, 6, and 3. The mean equals? Yeah, I asked a question like this on the last quiz. What's the mean of this data set? You got 8.5?
If it was on the test, then it was 8.5.
12, 3, 2,
Oh,
15,
never mind.
12,
I
9,
agree.
8, 12, 6, 3. Well, you just add all these guys together.
8.2.
12 plus 3 plus 2 plus 15 plus 12 plus 9 plus 8 plus 12 plus 6 plus 3.
8.2.
How many data sets are there? How many data sets?
8 to 10.
10. There are 10 values here. I add them all up, divide by 10.
8.2.
I get 8.2.
Yeah.
That would be the mean. So that sort of gives the idea that if I were to plot a graph here and draw a line graph, the peak would happen around 8.2. Right? That's sort of where the values seem to cluster together if I were to draw a picture of them. Right? Well, according to this approximation, right, we don't actually know. But this is just an approximation for that value. Another kind of average that we talk about often, the mode.
That's an average.
Yes. Not gonna lie to you, it's very rarely used. There are not many situations that you use the mode, but everyone always talks about the mode in a statistics class. So.
Yeah, where would you use the mode?
Well, what is the mode?
The ones that appear the
Repeated
most?
number.
Right, this is the value. That appears most frequently. So did I do this example for the same data set?
Yes.
Okay, so example, for the previous data set, what is the mode?
12.
Your mode equals 12. So according to this approximation of an average, the typical value is actually 12, which sort of doesn't seem to make sense here. Right? The only situation where something like this would make sense is if the vast majority of people have a certain value. And then you have like one or two that don't have that value.
Like in
Then you'd say that the typical value is blah, because like 99% of things have this value, and then there's just this 1% of things that don't, right? So you'd really have to have an overwhelmingly unanimous statistic for this to be a useful measure of the typical value. But in general, it's not. Yeah.
What if you had two numbers?
Then you
You add and divide.
You get the mean of the
Is that
mode.
like a
Huh?
protocol?
Yeah, I don't think
No?
have that.
I think it's called a bimodal or something. I swear.
There's some conventions that would say all numbers are the mode, and then there's another convention that say it's undefined, if the values are different.
Okay.
So you wouldn't ask that.
No, that's kind of silly.
You're welcome.
Another value, another kind of average that's very, this one's actually useful that you use it all the time. The median.
Yeah, that's very interesting. It sounds pretty cute. Now you're kidding.
Right? Not every time do we want to take an average to be the mean, right? There are a lot of times where the median is actually a better estimation of the median value. So this is,
Did you have to organize it?
right, this is the middle value when data is organized.
Yeah.
When data is organized in, it doesn't matter if it's increasing or decreasing order, you'll get the same thing, but let's just say increasing order. It's organized in increasing order. If there are two values in the middle, you
Yeah.
actually find the mean average of these values.
You know how his father, my middle school math teacher, he said, when you're angry, you give people the needle finger and then median. It's still so funny.
If there are two values in the middle, then the median equals the mean average of these two. Did I do an example for the same data set? Yes. So for the above data set, so notice that when you're looking for the mean, you have to first arrange them, right? You have to arrange them in increasing order. Arrange is probably a better word than organize, but whatever. Arrange them in an increasing order. So that's what I'm going to do here. So I went back to the previous list and actually rearranged it. 2, 3, 3, 6,
8.
8,
8,
9,
9,
12,
12, 12,
15,
15. And so what's the median here?
8.5.
Start. You can do this cross off the ends thing if they're not a lot.
4, 5.
And then we end up with, there would be 2 people in the middle.
8.5.
So I take 8 plus 9 over 2, and that gives me 8.5. So the median is 8.5.
Yeah.
So how many numbers were there? There were 10?
There are 10, yes.
Right. So another way to do it is if there's an even number, you can take the number of numbers and then divide by 2, and then take one more than that. So 10 divided by 2 is 5, so we know that the median would end up at the 5th number, but you'd have to average the 2. To do that, instead of crossing out. You could just divide by the number, half the data, which we'll do that approximation later as well. We'll actually put that into practice. What else?
Yeah. 8, 12, and 5.
I figured I'd mention an example. When is the median used? Where's the place that you guys often see median?
Salary.
With salaries. You ever notice, why don't they tell you the average salary? The mean salary?
Because it's so skewed. Some people might earn $100,000, some people might earn $10,000.
Exactly. So if you look at like the average corporation, you might have a few fat cats over here making like hundreds of millions of dollars. And then you have tons of little thousands of people earning like $30,000 a year, $50,000.
You mean like the
now, if you were
1%?
supposed to take the mean average of all those salaries, because these guys' salaries on this side, which is just a few of them, is so large, the mean is going to be somewhere in the middle. It's going to be like, holy crap, the average salary at this company is like $1 million. Like, when it's really not, right? Most people make nowhere near $1 million. So that would not be a good approximation for the typical value. So that's why they look at the median. They just line up all the salaries and they pick the guy in the middle. And it's actually a better approximation for what can you expect in the typical basis to get paid working for this company. So when is the median used? Salary is one example.
Determining the middle class.
Yeah, because you have that 1% and the 99%. The 1% has most of the wealth. You can't really average it. So in class, so things like that. So situations where
Improbable.
I didn't define this phrase I want to use yet.
Both types of classes, right?
I'll just say it right now. Situations where a few outliers.
Oh, I know what outliers are.
It's a technical term. I should define it.
I'm kind of dancing.
Skew a mean average.
Joanne taught me that.
So any situation where there are few values that are so large or so small in comparison to all the other values that including them in an average calculation would just mess things up and not really give you the correct information, you might use something like a median average, right? So the mean average is not always what you should use. An outlier, this refers to a value that is much larger or much smaller than the typical value in a data set. So sometimes your outliers are so out of the typical range that taking a mean average would not be useful to you. And so you might do something like a median, right? A mode is very rarely used. By the way, I should also mention when a mean is useful.
Joanne, I have a question.
Yeah?
Are you going to cover p-values?
No. I think that those are in chapter 15. We're going up to chapter 14.
Oh,
But we could continue if you guys want.
As long as it's not on the test.
Yeah.
What do you know? So the mean is useful for symmetric or bell curve data. Right? So the salary in a large company might look like this. Right? You just have a few guys over here making most of the money, and then you have the vast majority of people here taking up everything else. Right? So something like this, the median is probably a better average. However, if you have something like this, like symmetric, like right through the middle, the mean would be a better average to use. Right? It turns out, though, that by far more things in nature follow this kind of pattern. Right? Not everything, but a lot of things. A lot of the things we care about follows this pattern.
Like in genetics.
And so that's why every time someone hears the word average, they think of the mean average. It's because it's so common. It's not the only average, but it's such a common average to use. I want to talk about variation next, but I'm not gonna have enough time to talk about that. Yeah, so remember the whole idea why we started this statistics thing. There were some big questions that we wanted to answer, right? That we didn't know the answer to. Like there was no real math equation to answer this. So what we do is we collect data, lots of data over a period of time. And we study this data, we organize it, and we try to find patterns that will help us answer our questions. So we might start by throwing things in a table, but then the tables got too big, and then we started drawing bar graphs and bar charts, then line graphs, and then those started getting too complicated with all these bins and stuff. So we did is start drawing shapes, the shape of graphs. And it turns out that just by knowing what the shape of graph is, gives you a lot of information, and we can start to figure out where are the parts of the data that we should be focusing on. Usually the peaks are a nice part, because they tell you what happens typically, right? So when you say something like, does smoking cause lung cancer? You're going to want to study where most people fall, right? There's like one guy in this village out in nowhere that could smoke and he has great lungs. Okay, that's cool, but like millions of people over here, right? You always are going to want to look at the peak. And so finding out that peak value is going to be a very important thing. That's where averages come in. And that's where the mean, median, mode will come in, actually analyzing this peak. Next time we're going to talk about variation, where you're going to realize that sometimes just going after the peaks is not as easy as you might think, and it actually doesn't give you as much information as you might think. And so variation, talking about how data spreads out, is one other way we can look at data. We're going to talk about standard deviation and all that good stuff. But that's for next time, after the test. So yeah, so test is Monday, covers chapters 4, 5, and 6.
Is it going to be 1 hour 15?
Yeah, how long?
An hour and 15. So it's the same length as last time, 5 problems, 15 minutes each. I have your tests if you want to take them back.
Yes. Homework? You collected homework?
Yes, collecting homework. Give me the homework.